Hello and welcome to this next lecture in the course on pattern recognition. This talk will mostly discuss a few issues related to assessing what we learned correctly or not, more than any specific algorithm for learning classifiers. So, let us just step back and take a look at what have we done so far. In this course, what we have done so far is that we discuss many different learning algorithms, right? The various techniques starting from perceptron or starting from Bayes classifier with estimated densities. We have seen various learning algorithms, various methods for learning classifiers. Now, given so many methods and let us say on a specific problem, we got some examples and we use one of the methods to learn a classifier. Then one thing that is certainly needed is we need to know how to estimate the accuracy of the final learned classifier, right. So, we are learning from some finite data. So, while maybe many of the algorithms have some kind of optimality proof that is mostly asymptotic. So, we somehow need to estimate whether what we learnt is good enough for our application or not. Okay. Now, that is one aspect that we will look at. How do we assess the correctness or otherwise, or assess the level of performance of the learned classifier. But before going there, we will look at some general issues in classifier learning that have nothing to do with the specific method you are using. No matter what method you are using, there are some generic issues. Now, the first question that we may want to ask along the general issues is what is a good method, right. We studied many algorithms. We started with Bayes classifier, then we said if you know the class conditional densities, then Bayes classifier is the best you can get. But then we said of course, we do not know the class conditional densities, who will give to us. We said, but we have data, so we can estimate class conditional densities. We studied various methods for estimation. Then we said, but the estimated densities may have a lot of errors and we do not know how those errors affect the goodness of Bayes classifier. Then we said, can we directly estimate classifiers? We looked at discriminant functions, both for classification, regression. We looked at linear techniques, we looked at perceptron, LMS, least squares methods, Fisher discriminant. Then we went on to look at nonlinear classifiers, neural networks, SVMs. Now, in the course, a progression from simple methods to more difficult methods. The last classifier algorithm we learned is the best classifier algorithm. Then what is the purpose of learning the others? Right. So, in general, but having studied so many different techniques, before the course is over, we should ask what is a good method, right. So, for example, as I was saying, can we say that SVM always learns the best classifier? Now, of course, whenever we consider different methods, we have discussed many practical tips about when different methods are suitable. When would I use a least squares based linear regression? When do I use a nonlinear regression method? When may I want to use SVMs? When may I want to use neural networks? But these are some level of practical tips, and we have discussed this enough through the course. But one thing that we would like to emphasize, because we are reaching the end, is that in a fundamental sense, no method is best for all problems. The reason we studied so many methods is that each method has its own niche where it will perform well. Well, it is very difficult to completely characterize that niche and say that if in this PR problem use this method. Of course, if you could characterize that, there is no scope for scientists working in machine learning and pattern recognition. But while each method, each algorithm has its own niche in the application space, in a very fundamental sense, we can never say one method is the best or one method is definitely better than some other method, and so on and so forth, right. And this in a very fundamental sense. So, we will first start from here, right. So, that we will not think that there is a God given method or a panacea for all pattern recognition problems, right. That there is no single algorithm that will do on all problems. Okay. So, we can talk of this as inherent superiority of a method. A method could be a an SVM with a specific kernel function with specific values of parameters and so on and so forth. We can say a classifier learning algorithm is inherently superior to another algorithm if the first one always learns better classifiers than the other. If you think always is a little too strong, let us say most of the time in most pattern recognition problems that you may encounter. For most pattern recognition problems, if one method always learns superior classifiers to the others, then we can say this method is inherently superior to the other. As it turns out, there is no algorithm that is inherently superior like this. What does that mean? If an algorithm does better on some pattern recognition problems, on certain kinds of application problems, if it is doing very well compared to another method, if it works much better, it learns better classifiers. What it would mean is there would be other instances of pattern recognition problems where it will do worse than ours, because even on most problems it cannot do better than any other method. Right? So, what we are now going to say is there is a very formal way of saying this. We will at least look at the statement of this formal theorem. We will not be able to prove this, but we will look at the statement of the formal theorem that captures this thing that no classifier is inherently superior. Okay. So, what we are going to do is that there is no way I can say one classifier is inherently superior, and we will say it in a very formal sense. As a matter of fact, we will say it as a theorem. Okay. So, now how do we compare methods? We will agree to compare methods. So, maybe we will give the same training data to two different methods, and each method will output a classifier, and then we can compare the methods by asking the classifiers output by the two methods, how do they perform on patterns outside the training set. This seems fair enough, because both methods are given the same training set, and then they can use the training set any which way they want, and then they will come out with a classifier. Once they come out with a classifier, we are saying we will test that classifier on all patterns outside the training data training set, and that is how we will compare the errors of classifiers learned by two different methods. Okay. So, let us put some notation. Let as earlier script D denote the training set, and let us say n is the number of training examples. We will keep n fixed throughout the discussion, and let us say f denotes the target function, that the training examples actually come classified through f. So, f is the target function. So, we will think of it as classifier or regression, it really does not matter, there is a target function that we are learning. Let p subscript k of h of x given d denote the probability that the classifier learnt by the kth algorithm using training data d would say h of x on a pattern x. When for the kth algorithm, if you give training data d, it will learn some classifier, and that classifier when given x would say hx. Right? That is the probability of it happening. This essentially what it means is, let us say p k h given d is the probability that the kth algorithm learns the function h given data d. So, if this is the probability of kth algorithm learning h, then p k h of x given d would be the probability that it will say h of x and x. Okay. Now, of course, given an x, my learning algorithm will say h of x with this much probability, whereas the true output is f of x. So, how can I define the error? So, let us say j k f comma d, k is for the kth algorithm, the target function f is fixed, that training data set d is fixed. So, for a particular target function f, given a particular training data set d, with the kth pattern regression algorithm, let us say j k f comma d with the expected error of the classifier learnt by the kth algorithm using training data d with target function f. Okay. Now, how can I give this? So, j k f d on x, and as I said we already agreed to, first let us consider the inner summation. We already agreed to measure the errors on x which are not in the training data. So, I sum over all x not in D. A particular x will come with probability p of x. On x, my algorithm will say h of x with probability p k h of x, and this tells you whether this is right or wrong. Delta a comma b is 1 if a is equal to b, 0 otherwise. So, if f x is equal to h x, there is no error. If f x is equal to not h x, there is error. This is like a 0 1 loss function, right. So, and I am summing over h because my kth algorithm may land different h with different probability, right. Because if the learning algorithm is deterministic, what all the learning algorithms we consider so far are mostly deterministic, then given a particular training data set, because the learning algorithm is just a computer program now, given the same data set, it will always learn the same function, which means given a D, my what I call pk h given D, that is probability of my algorithm learning h, is non-zero only for one h, because given the same D, it will always learn the same h. So, pkh given D is non-zero for only one h, that means on a particular D, a kth algorithm learns only one particular h. So, this h summation can actually go, but writing like this is much more general. Even if the algorithm with the same D with different probabilities it outputs different h's, then also this expression is right. But because most of our algorithms are deterministic, I do not need the summation with respect to h, and this then is interpreted as given D, I use that h here in this expression, which will be lent by the kth algorithm. Okay. To say that I use that h which will be lent by the kth algorithm is what this 0 1 factor is, pkh. This is for deterministic algorithms. Okay. So, any case, kth algorithm learns h with probability pk of h given D with training data D. So, on an x, the probability that the classifier land with kth algorithm will say h of x is this, and this is the error of saying h of x, 1 minus delta f x from h of x, weighed by the probability of x. That is my error, summed over all x not in the training set, and I have to sum over h because of this probability. As I just now said, if the learning algorithm is deterministic, for only one h this is non-zero, hence effectively the summation, the outer summation will reduce to only one h. Okay. Now, the formalization of the fact that there is no inherently superior classifier is called no free lunch theorem. Right. This is an American colloquialism that no free lunch means if somebody is offering you a free lunch, it certainly means that he wants some work from you, right. He or she wants some work from you. So, there is no such thing as a free lunch. You never get in this life, you never get something for nothing, right. So, that is what this theorem says, and once we complete the statement of theorem, we will come back and see why it is called no free lunch. Okay. The no free lunch theorem is a formalization of the fact that no learning algorithm is inherently superior. What does the theorem say? The theorem says the two parts of the theorem. The first part is for any two learning algorithms, we will call them 1 and 2, we will talk about kth algorithm. So, let us say any two learning algorithms 1 and 2, this quantity is 0. What is this quantity? It is product of one term is probability D given f for a given target function, or the probability of generating a data set D, into j1 f comma D minus j2 f comma D. This is the difference in the error rate of the two algorithms when given D, weighted by getting D for training, summed over all D, right. This is the expected error over all possible training data sets that I may get if f is the target. Then I summed over all f, which means uniformly over all f. If I assume that all possible target functions, all possible pattern recognition problems are equally likely, then this outer summation will have some whatever, because every problem is at the same weight, the weight does not matter. So, summed over all possible f, right, this is 0. So, let us say it words average, as I said, we are always keeping my training set size fixed in all this discussion. So, as I noted here. So, average over all size and training sets and uniformly averaged over all targets f. This uniformly is very important because there is no weight for different f's, all f's have the same weight. Averaged over all size n training sets and uniformly averaged over all targets, the difference in the expected error of any two algorithms is 0, no matter what are the two algorithms. If I average the expected error over all possible target functions uniformly, average it uniformly, then the expected error is 0. A matter of fact, the second part says that it has nothing to do with the training data set per se. I can even keep d fixed if I want. For a particular training data set, uniformly averaged over all possible target functions, meaning all possible pattern recognition problems, the expected difference in the expected error of any two algorithms is 0. So, if we uniformly average over all problems, all algorithms are same. No one algorithm is any better than other, right? That is what it means, because this is the expected error of algorithm 1, this is the expected error of algorithm 2. You take the difference and uniformly sum it over all f, whether you can either fix the training data set or weigh the weight with respect to training data set like here. But in either case, if you uniformly average over all possible functions f, the difference in the expected error of any two algorithms, it really does not matter what the methods are. Of course, one of the algorithms might be arbitrary, right. It may always give you the same function irrespective of the data. I am not saying anything about what kind of method this is. No matter what the two methods are, the expected error, the difference in error is 0. If we uniformly average over all problems, all algorithms are same. No one algorithm is any better than the other. That means no inherently superior classifier design strategy exists. There is no method which allows you to learn a classifier that is inherently superior to any other way of learning a classifier. Any other meaning? An arbitrary way of learning a classifier is not inferior in our inherently superior sense, is not inherently inferior to any other algorithm that we already know or would ever discover. So, what does this mean? Means a specific learning technique may be good if you are interested in a certain subset of PR problems. If you think of a set of all possible PR problems, if in some subset one algorithm does much better than others, then it must be doing much worse than others in some other part of the space of all possible problems. The only way I can do better on certain class of problems is by doing worse on certain other problems. If all problems are weighed equally, then average over all possible problems, the error is one algorithm is no different from any other algorithm. So, any specific algorithm essentially has a niche space and it is exploiting the characteristic of that subset of pattern recognition problems to do better on them, and the price we pay for it is that because we are tuning the technique for some special property, special structure that class of pattern recognition problems may have, we would be doing badly in some other part of the space of all possible pattern recognition problems. It is in this sense, it is called a no free lunch theorem. If an algorithm is able to do better than other algorithms on certain problems, it is able to do like that only by doing worse than other algorithms on some other problems. Right? You cannot get good performance on certain problems without paying the price of bad performance on other problems. That is why there is no free lunch. Okay. As I said, we can't prove the theorem, but we can look at some comments on what it could mean, and also we will look at it in a simplified example setting of Boolean features, so that you get a sense of why it happens. At this stage, it may look a little counterintuitive. At the end of a tough pattern recognition course, if I tell you, no algorithm is better than any other algorithm, not only that no algorithm is better than any other algorithm, all the algorithms I am teaching are no better than any arbitrary method anybody can think of. then what is the purpose of all this? Well, remember that no algorithm is inherently superior when uniformly averaged over all problems. Right? No algorithm is inherently superior in terms of expected error only when we uniformly average over all problems. If every possible, every conceivable pattern recognition problem is of equal importance to us, only then no algorithm is inherently superior. The space of all PR problems, if the algorithm does well in some region, is compensated by bad performance in some other region. That is all the theorem says. It does not say that an algorithm cannot do better than others in one particular region. Now, if you think every problem is equally important, then obviously there is nothing to learn from examples. Let us think of a two-class problem. Every pattern recognition problem is simply one particular subset of real line. If on different days I am asked to learn different subsets of real line and every subset of real line is equally important to me, then I cannot have any general strategy of learning. We already seen that, right. Only for example, I am learning axis parallel rectangles, then I can make a very nice efficient algorithm. But that is good only if I know beforehand that I am interested only in axis parallel rectangles. On the other hand, if I am interested in learning every conceivable subset of real line R2, then obviously it is very difficult to learn from examples, right. This is something we already know roughly, but the no-free lunch theorem nails it down completely. That is, in terms of expected error, if we average over all possible PR problems, no algorithm is better than any other algorithm. Let's see what it means in a very simple setting. Okay, then it does not look so counterintuitive. Let us say we consider a problem with just 3 binary features. The 3 features x1, x2, x3, a feature vector dimension 3, and all features are binary. Okay, so essentially my space has only 8 possible feature vectors. Let us say this is my training set. So I am shown some 5 patterns. So these are 1, 0, 0, 0, 0, 0, 1, whatever. Okay, these 5 patterns I am shown. This is the values of the target function, and let us say some h in my space have the same values. I have a h that is consistent on the training sample. Now, obviously, I may use some method to learn. Of course, I may output a function that is consistent, may not output a function that is consistent, but I know the target function value. So, let us assume there is no noise. Now, what is it I am interested in? I am interested in asking, if I learn this h, how will it perform on unseen data? So, some pattern that is not in the training set. Of course, my fx has some value. What will my h say? Right? I am not really bothered about values in training set. Of course, here I may choose that they are same, but I am essentially interested in how will h perform on unseen patterns. Right? In this particular case, there are 3 unseen patterns. Right? So, 5 are in the training set. So, only 3 unseen patterns are there. I am asking every h we are going to evaluate based on how well the predictions of h match the predictions of f. But it is not that, we are going to average this error over all possible f. How many such possible f are there? Here there are a total of 8 possible feature vectors. 5 of them are already in the training set. So, there are only 3 feature vectors outside the training set. So, each of these 3 features, so how many different f's can I have now? The f has to have these values for on the 5. So, what are the possible f's over which I will be comparing? All f's that can take different values on these 3. So, how many such f's are there? 2 into 2 into 2, right? There are 8 such f's are there. So, there are 8 Boolean functions consistent with the training set. Those are the only ones on which I will be finding the errors, because we are finding the error only on x, not in the training set, right. Now, as all of you know from such Boolean functions, that if I look at all possible Boolean functions for this 3-row truth table, then obviously on any one row of the truth table, half the functions will be 1, half the functions will be 0, right. That is how the Boolean functions behave. So, on any of the 3 patterns outside the training set, half these 8 Boolean functions would take 1 and the other half would take 0, which means on each of those patterns, irrespective of whether hx says 1 or 0, see at all that the different learning algorithms can affect is whether that the corresponding hx will say 1 or 0 on these 3 patterns outside the training set, and irrespective of whether my hx says 1 or 0, half the time is right, half the time is wrong if I average over all possible f, right. So, my algorithm can do nothing, all my algorithm can do is give me a h which can only decide to say 1 or 0 on each of these patterns, irrespective it says 1 or 0 on any one pattern. Its error when averaged over all f is always 0.5, right, because half the patterns its prediction will be right, half the functions is for half the f its prediction will be correct, for half the f its prediction is wrong. So, the fraction of f on which it will predict wrong is always half, irrespective of what h is. This is essentially what the no-Prion theorem says. No matter what h is, averaged over all these f, its error is the same, and hence no learning algorithm is better than other if we average over all f. On the other hand, let us say all f are not equally important to me. Let us say when I started learning, when I am given this problem, I was also told that the target function is a single min term, right. A min term, as you remember from your Boolean algebra days, is a conjunction of literals, right. In general, you write sum of products form. So, each term is called a min term. So, let us say the Boolean function that I am interested in can be represented by a single term, a single conjunction of letters. This is the, so, I am only interested in learning Boolean functions that can be represented as a single term, right. Now, that is quite a structural constraint. Without going into details, of course, looking at this table, those of you who are interested can verify, given this training data, the fx values, you can ask how many possible min terms are, how many possible single min term functions are consistent with this data, right. I will not go into the details, it is a very simple thing to do, but one can show that the training data is consistent only with this one particular function x1, x2 bar, which means if I am working in the space of functions that can be represented by a single min term, that is the only niche of pattern recognition problem that I am interested in. Now, all algorithms are not same, because there is only one function that is consistent with all training data, right. That is the function I must be having, because I know beforehand that the functions over which I am learning are single min terms. So, this is the only min term that could be generating data. So, if I average over all f, this is all f that satisfy this structural constraint, there is only one function, and hence a h that predicts as per this function will have 0 error, every other h will not have 0 error, and hence one method can be superior to other if I restrict my attention to learning only those target functions which can be represented as a single min term. Now, this essentially is the sense of no-Prion theorem. When you are interested only in this subset of your problems, a learning algorithm or not all learning algorithms are same anymore, right. Otherwise, if you are interested in all possible target functions, obviously there is no algorithm can be superior to another. Okay. So, this is the sense of no-Prion theorem. So, there cannot be an algorithm that does very well on some set. Let us say it can't even have algorithm that do very well on some subset and do average on the rest. That is not possible, because if they do very well on some subset of pattern recognition problems, then what the no-Prion theorem assures us is that they do very badly, not average, they do very badly on some other subset of pattern recognition problem, because uniformly averaged over all pattern recognition problems, no algorithm is different from any other algorithm. So, if there is an algorithm that does very well compared to another algorithm on some subset, then this algorithm will do very badly compared to the other on some other subset of pattern recognition problem, right. So, depending on the problem on hand, we may have to choose an algorithm, okay. But while this is in general true as a general tip for how one makes pattern recognition systems work, it is also true in this fundamental sense that is not just because we don't know enough, we have not yet found the ideal pattern regression learning algorithm. There is no such a thing as an ideal algorithm for learning classifiers. Such a thing does not exist. That is what our no free lunch theorem guarantees. No free lunch theorem is to say that there is no best classifier learning strategy. Right? So, that is nice. It is not as if we should be searching around for this one algorithm after which we can stop working on pattern recognition problems. So, depending on the kind of problems you have, we have to find some algorithm that works best for the problems of interest to us in that application. In the same way, there is no such thing as the best features. There are no God given features for any problem. Not for any problem, there are no God given features. Once again, in a problem independent sense. That is, if all problems are equally important to you, then one feature set is as good as any other feature set. It really does not matter. Right? For once again, uniformly average over all problems, no feature set is better than any other. This can also be proved. I won't even state this because it's a little more complicated to state it precisely. This is called ugly Duckling theorem. The origin for the name is that all of us think that ducklings are very ugly. As a matter of fact, duckling in English language is used as a kind of symbol for ugliness. But obviously, I am sure the duckling's mother won't agree that duckling is ugly, right. So, the ugliness is in the eye of the beholder. So, that is what it says, that there is no such thing as the right feature set. Right. If all problems are equally important, then no feature set is better than any other. Okay. This theorem is called ugly Duckling theorem. Anyway, I said we are not formalizing this. So, this is one generic issue about classifier design. So, we understand now that there is no inherently superior classifier design strategy. Okay. Now, a few other generic issues. So, the entire idea of learning is the following. We are given a set of IID examples, and then we are asked to learn a classifier, or we learn a classifier or a regression function using these examples, right. A linear regressor or a nonlinear regressor, or in general a function or a classifier. We given training examples, we learn a classifier. This is the whole idea. This involves two steps: learning a classifier or a function given training examples, as we seen through the course, involves two steps. What are the two steps? I mean, two broad steps. One is that to first select a suitable class of models, linear functions, a neural network, or nonlinear function represented through a kernel, or what have you. I choose a suitable class of models, and then I learn a specific element of that class, a specific model, specific classifier from that class, right. So, there are two issues involved. One is I have to first decide over which class of models I learn, and then within that class I learn them. So, the first one is called model selection, and the second one is called model estimation. What we studied throughout the course are algorithms for model estimation. Backpropagation is a method that if searches over a specific class of neural networks and gets to the one that has the least error. Right. Each of the algorithms that we considered are essentially model estimation algorithms. Right. Of course, various points we said, how do I decide the model, how do I decide how many hidden nodes to have my neural network. So, that is the issue of model selection, right. So, for an example, suppose you are learning a neural network model, right. What does model selection involves? It involves choice of the network architecture. That is, let us say I have to first choose the number of layers, one hidden layer, two hidden layers, so on. Then I have to choose the number of hidden nodes, I have to choose activation functions, then we have to choose the parameters in the learning algorithm, all this. Right. All this is part of the model selection. So, choosing a set of hidden layers and hidden nodes in each hidden layer will give me one particular class of neural networks, one particular class of classifiers, one particular class of models. Now, within that class, within that family of classifiers, we are minimizing mean square error, we are minimizing empirical risk using squared error loss function to learn a particular class. For example, using backpropagation, we learn optimal values of weights etc., which means we are picking out one of neural networks or that structure, right. This is the model estimation. For another example, if I am using an SVM, the choice of kernel function is part of the model selection. I have to decide whether I want, let us say, polynomial kernel with p is equal to 3 or polynomial kernel with p is equal to 4, so on. So, that kind of decides which family of classifiers, which family of models I am searching over. After I have chose that, for example, after I choose the kernel function, then the optimization algorithm does the model estimation, right. So, whether or not it is explicitly stated like this, all our algorithms involve both model selection, I mean essentially model estimation, but we have to also do a model selection, right. Of course, we do not know whether the selected model is the right one. We already discussed at various stages that the model is too complex. For example, neural network has too many hidden nodes, if the VC dimension is very large, then we may be doing overfitting, right. The generalization error of the length classifier will be poor, it will not do well on unseen data, right. So, model selection is a very crucial issue, because depending on the kind of function we want to learn, depending on the amount of data we have to choose the right model, right. How do I do model selection? Now, some generic issues about what this model selection means. Okay. This is often seen, there are many different ways of seeing it. In this class, we will consider only one, which is called the Bias-variance tradeoff. Estimating a model is very similar to parametric density estimation that we considered, and when we discussed the parametric density estimation, we saw that the mean square error of an unbiased of an estimator is given by the sum of its variance and bias square. We showed that the mean square error of any estimator can be written as bias square plus variance. Right. So, essentially very often there is a trade-off between them. I mean, we may not be able to reduce the mean square error very much. The model selection may be trading of bias versus variance, or in very nice scenario may reduce both. Now, this kind of bias variance decomposition is crucial in many learning problems. Okay. And essentially what it means is the following, as we have seen this enough number of times in this course. If the class of models for which I am searching is too complex, then if I average over all possible training data I may get, I would by and large get the right function, because the model class is very rich and the target function or a very close approximation to it exists in my bag. So, that is essentially what low bias means. But because it is very complex, on most realistic size data sets, I may not be able to do a very good job of learning, and hence depending on the examples I have given, I may pick out different functions, and hence variance would be very high. So, let us just look at this in a little more detail, what this bias variance decomposition is. Once again, to keep things simple, we will look at it in a very simplistic scenario. Let us say y denote the target random variable that you are that you want to predict, the class label or the function value in a regression problem, and let us also assume that the relationship between the target and the feature vector x is y is equal to f of x plus epsilon, where epsilon is the zero mean independent noise, simplest of problems. So, f is essentially the target function. I want to learn the target function f given that training data which are x comma y, where y is f of x plus epsilon. Okay. Let us say f hat is the function output by the learning algorithm. Okay. Now, let us say I want to ask what is the expected error in the prediction made by our learning algorithm, that is prediction made by f hat at a specific point x naught, let us say. So, the error let us say we will take the mean square error. So, error at x naught is expected value of y minus f hat x naught whole square, where the y is with respect to an x which is equal to x naught. That is why I put condition x equal to x naught. So, we already know when x is equal to x naught, y is f of x naught plus epsilon. So, I can write this as f of x naught plus epsilon minus f hat x naught whole square. Now, I get an epsilon square plus f x naught minus f hat x naught whole square. The cross term will go because the cross term contains epsilon into f x naught minus f hat x naught. Epsilon is independent of all this. So, expected value of the product will be expected value of epsilon into some term, and expected value of epsilon is 0 because epsilon is 0 mean noise. So, the cross term will go away because noise is 0 mean and independent. So, when I expand the square, I only get expected value of epsilon square and expected value of f x naught minus f hat x naught whole square. Now, if you remember what the same algebra that we did for a parametric point estimator, I can rewrite this term as follows: f x naught minus f hat x naught whole square. I have added and subtracted expected value of f hat x naught. So, I wrote it as f of x naught minus expected value of f hat x naught plus expected value of f hat x naught, and then grouped these separately. Why? Now, if I do this square, I get this square f x naught minus expected value of f hat x naught whole square, then this square expected value of f hat x naught minus f hat x naught whole square, and a cross term. A cross term is inside the expectation. The first factor of the cross term f x naught minus expected value of f hat x naught is constant, because f x naught is constant by definition. This is expectation of something, so this is also constant, that comes out of the expectation. Then the second term is expected value of f hat x naught minus f hat x naught, and when I put expectation outside of that, that will be 0. So, the cross term will be 0, thus giving me sigma square epsilon, expected value of this square and expected value of this square. Okay. Expected value of this square is f x naught by expected value of f hat x naught whole square. I do not need expectation because they are constant. The second term is expectation of this. I have just wrote it the other way, so that it looks familiar. F hat x naught minus expected value of f hat x naught, because the square anyway does not matter. Okay. So, this is what I get finally. So, this is what we can write as, this is the inherent error because of the noise variance. This is the noise variance, because my the data given is f x plus epsilon. So, whatever is the variance in epsilon, that is the minimum error I have to make anyway. Then this is the bias. This term is called bias square, okay, and this is the variance. This we already know, f hat x naught minus expected value of f hat x naught whole square. Expectation is nothing but variance of f hat x naught. This is called the bias of f hat x naught. What does bias tell us? Bias is the difference between f of x naught, the actual target function, minus expected value of f of x naught. What is this expectation with respect to? Obviously, my training data sets. On different days, I get different training data sets. Average over all training data sets. So, f hat is a function of the training data. So, f hat is random only because it is a function of the training data. So, this expectation with respect to the training data distribution. So, average over all possible training data sets, do I on the average make the right prediction? So, bias is about how well on the average the learned function captures the true underlying function. Here of course, we have written error at a particular point, but essentially we are interested in error at all the other points. So, essentially it is a matter whether the expectation of f hat is the same as the function f. So, bias is about how well on the average the learned function captures the true underlying function. Right. What about the variance? Variance tells me, so expected value of f of x naught is what I learn average over all training data sets, whereas this is what I learn on any one, so to say. So, this tells you how much variance is there, how close would be predictions of the learned function would be over all training sets. One day I learn with one training set, so I learn one function that makes some prediction. Another day I learn with another training data set, hence I learn another function that may make a different prediction. I am asking how different are these predictions. If the predictions are close together, the variance will be small, predictions are different. Right. So, the variance is about how close would be predictions of the learned function or training set, because that is important, because I will essentially learn with only one training set, right. I can't average over all possible training sets. If the class of functions over which you are setting is rich enough, there is likely to contain good approximations of the target function, and hence average over all training samples, we may learn a function that is close to the target. So, if the class is rich enough, our bias is likely to be small. But the model class is rich, unless you have very large training sets, we may not learn very well. In the sense, on any given day with the given training data, I may not be able to learn the same function. So, on different data sets, we may learn different functions, and thus we may get high variance. This is the whole idea of the bias variance decomposition in the final error we make. So, low model complexity results in high bias. Right? If the model is very restricted, I may not be able to find a function that is close to the target function. So, I may have a lot of bias. So, if I am learning a 10th degree polynomial using linear models, obviously even the best algorithm can only give me a linear function. So, my model complexity is very small. So, there will be a lot of bias. So, we can say high bias indicates poor estimate. I have not chosen the right class to look for the function. High model complexity on the other hand will have low bias, but will result in high variance. Okay. So, we can say high variance indicates a weak estimator, because we do not have the power to estimate from such a high model complexity unless you have very large number of examples. Okay. So, once again we look at this in a very simple example. Suppose my learning method is a k nearest neighbor method. I am thinking of it as a regression. So, what it means is my f hat at any given x naught is average of the k nearest neighbors I can find in the data set. The values, function values, the k nearest neighbors. So, I represent the nearest neighbors as x1, xk. So, their corresponding function values in the data set is y of l, right. So, if y of within brackets l is the lth nearest neighbor value, that is x of l is the lth nearest neighbor to x naught, then its value on the training data set is f x l plus epsilon, because training data set I get only noise corrupted values. So, average of all this is what my predictor would be if I am using nearest neighbor algorithm. So, this is my prediction. Now, I have to find expect value of f of x naught. Right. If I put expectation here, what are the random things here? Of course, epsilon is random and xl is also random, because it depends on the training data set as to which are the closest to xl. So, to calculating this expectation is very difficult, because xl are random. Let us ignore it for now, right. If I ignore it, so I put an expectation outside, but I am not treating xl as random, then the epsilons will go away, because epsilons are mean 0. I get this. That means, between f hat x naught, which is this, and expected value of f of x naught, the only difference is epsilon, right, because we already seen that we are not worrying about averaging with respect to this, which you do not have to do. If there are enough training examples, then maybe they are distributed roughly around the same way. So, then epsilon is the only difference between the expected value of f of x naught and f of x naught. So, the variance is very simple, variance of f of x naught, expected value of f of x naught minus expected value of f of x naught, the difference is only epsilon. So, this is L is equal to 1 to k is because I am summing over k nearest neighbors, and this square. Essentially, it has to be epsilon k, in the sense it is the error random variable that corrupts the noise random variable that corrupts the k training, that particular training data. They are all anyway independent. So, all the cross terms will go away, and any single epsilon square term is nothing but the sigma square epsilon, and the square 1 square will make this 1 by k as 1 by k square. So, ultimately I get sigma square epsilon by k. What it means is, if I am essentially using a nearest neighbor estimator, variance decreases monotonically with k. This is intuitively very clear. As k increases, we are doing more and more smoothing in my estimate. I am taking average values of sufficiently many nearest neighbors of the current point as the estimate, and hence, irrespective of what data set I started with, if I am doing average of enough of them and the data is distributed well, then I roughly about get the same value. So, as k is increased, I do more and more smoothing. As a matter of fact, if k is equal to my data size, I always give you the same value. Right? One can show this is true even considering randomness of xl in general. However, if we smooth too much, the predictor value is likely to be far from the target, giving rise to high bias. So, if k is very large, as I said, if I do k nearest neighbor classifier and k is equal to the number of training data, no matter what the feature vector is, I always call the same class. Right. So, if I smooth too much, obviously the predictor value can be far from the target, giving rise to high bias. We get low bias if k is small. If k is equal to 1, we are not doing smoothing at all. we get very low bias then, but then we get high variance, right. So, this is essentially the issue, it always comes in various guises in different algorithms. So, such a bias variance trade-off is common in most learning methods. Okay. So, in general estimating bias and variance of a specific method is difficult. The generic issue is if you have large number of training samples, then usually variance would be small. So, variance can be reduced by having enough training data. If you have large training data, there is generally no problem, okay, because your variance will be small. Also, if I have large training data, then I can choose a richer model class and hence reduce bias. So, in general that is fine, but very often we do not get large training data. So, if you want to reduce both variance and bias sufficiently, we need to have sufficient number of examples and also we need to have some knowledge of the target function, so that we can intelligently choose the model class. You want to choose the model class, so that we will have a function that is close to the target function, and at the same time the class is not so rich that we will not be able to learn it with the example that we have. This is often an art, but this is one way of looking at the trade-offs involved in designing a pattern recognition system. Okay. Now, let us finally come back to the issue of how do I assess a length model. We use a training set to learn a model, right, a classifier, but we are actually interested in how well the classifier does on unseen data, right. Its performance on the training set is of no consequence, even though all my learning algorithms are essentially optimizing based on the error on the training set, right. We consider this enough number of times, right from my first class I have been discussing this. This is the issue of generalization error. How well does a classifier learn from some data generalize? How well will it do on unseen data? Training data is of course also IID, but even intuitively the error on training set is not a good indicator of the generalization error, because I am picking my classifier to do well on the training data. So, obviously, it will do well on training data. Only some classifier that does well on training data is what I will pick up, and hence the error on the training set, which is called the training error, is not necessarily a good indicator of the generalization error, because even in a stochastic sense it is it. The error on the training set is the empirical risk. We already know empirical risk is not necessarily close to the true risk, which is the expected error on new test data, right. My expected on the new test data, if I take data randomly, is nothing but the true risk, where the training set error is the empirical risk. Now, for empirical risk to be close to the true risk, we need large number of examples relative to the model complexity. The model is very complex, then we may overfit. That's basically when the training error is small, but the test error is large, right. Basically, if the model is complex, I may be able to find functions within the model, which can do very well on the training data, but they are not really learning anything, okay. Now, this is a phenomenon that always happens, it is called the overfitting. That is, I get very low training errors, but when I see new data, the errors will be large. One example is when I use too many hidden nodes in a neural network. So, we can roughly represent it like this. Suppose we have a fixed sample size and we keep learning with the same algorithm in more and more complex model classes, right. What can model complexity mean? Suppose I am using neural networks with more and more hidden nodes. Given that, given sufficient complexity in the problem, what one can expect is the training error. Initially, if I choose models of very low complexity, training error is the red curve, the training error is large, that the error on the training set. But as I keep increasing the model complexity, right, I can keep reducing my training error, right. So, for example, if I am using RBF networks, once I reach the number of hidden nodes which is same as the training samples, I can get 0 error. So, while the shape of the curve, the specific shape of the curve is not important, the general shape of the curve, that at low complexity I will have high training error, but training error can be monotonically decreased as the complexity decreases. But if I look at the test error, that the error of the length classifier at any given model complexity at a particular number of hidden nodes or whatever, at a particular model complexity, I learn a classifier and ask how will it do on unseen data. If I track that error, that also initially decreases. As my model complexity is increasing, it initially decreases, but after some model complexity it starts increasing, because given your data, that is the level of complex models that you can learn. So, we need to select the model with the correct complexity. Only if you run our algorithm at a model complexity level of this, are we likely to get a good final classifier. Otherwise, we may get a bad final classifier here. So, this is a generic behavior of most learning algorithms. For the same training set size, as they keep increasing model complexity, till some level both training and test errors will decrease, but after that only training error will decrease, but generalization error will increase. So, of course, there is no way of knowing which is the right complexity. It is very difficult to decide on what particular model class is correct from a problem. Right? Model class means how many hidden nodes in neural network, what kernel do I use in SVM, so on and so forth. While we have seen some theory like the VC dimension and so on, these are loose bounds. They give, while they give you general guidelines, they can't give you any specifics. Hence, one needs to use the training data for doing model selection also, for deciding which model class to use. How do I do this? But we saw training error is not a good indicator for the model class, right. I can keep increasing the complexity and keep reducing my training error. Right. So, if we want to use the data that we have, then we have to use it slightly differently. If we have sufficient data, we can do this. We can do both model selection and model estimation. This is how we do it. We divide the data into two parts, a training set and a validation set. We select some model class, a specific class of neural networks, a specific a kernel function with specific parameters and so on, and then use the training set to learn the classifier, whatever best classifier you can get within that model. We find the error of the learned model on the validation set, not on the training set, but the other training data that we have, which I call the validation set. Now, I do it for different model class. So, I start with, let us say, a 3 hidden node network. I learn using my training data, and the final network, its error I measure on the validation set. Then I do it for 4 hidden nodes. With the same training set, I once again learn the best 4 hidden node network, and now calculate its error on the validation set. Now, I can plot the errors on the validation set of models of different complexity, right. So, if we do this for models of different complexity, we can choose the one that has the least error on the validation set. So, this allows us, for example, to use the training data to also learn, let us say, the number of hidden nodes in neural network. So, we divide the data, we use one part for training, one part for validation. The training is used for model estimation, the validation is used for model selection. Normally, we would also like to have an estimate of the final generalization error of the final learned model. After doing all this, I decide that okay, 5 hidden nodes seem to be best, and then learn the final 5 hidden node network. Now, if somebody asks me how well do you think this will perform, what will I tell him? Of course, I can find, this is called the model assessment. I can tell him that its error. So, my final error, I can say whatever is the error I got on the validation set, maybe my good estimate for generalization error, but it's overly optimistic. I picked that particular network because it is doing well on validation set. So, by definition, that network is tuned to do well on the validation set. So, what one does is that you have separate test data also for final assessment. So, what does all this mean? We need to use the data that you have for model selection, model estimation and model assessment. We divide the data into 3 parts, training set, validation set and test set. We repeatedly use the training set to learn specific model from a chosen class of models. The validation set is to select good model class, and test set is used to assess the final learned model. Okay. So, this is how one does model assessment. Next class, we will look at what to do. See, to do all this, I need a lot of data. I may or may not have enough data. So, we will look at some generic practices people use for doing model assessment in the next class. Thank you.